We have already talked a little bit about Bohr theory. We already know how to draw Bohr diagrams. We already know about some of the stuff that's on the title here. What we're going to do is we're going to move a little bit farther forward in that understanding so that we can start to make some sense out of how things behave and why they behave in that way. So specifically, we're talking about ions, octets, and the periodic table. So the starting point for this, or the things that we already know, is we know how to do Bohr diagrams. Maybe we haven't done a whole lot of them. Maybe you're still a little bit fuzzy on some of them, although honestly we only have to worry about the first 20, really only 18. We know how to do ions, or we know what an ion means. It means it has a charged particle. It is either lost or gained electrons. So there's an imbalance between numbers of electrons and protons, but it's always going to be the electrons that changes the number. So you can have a negative ion, in which case the atom has gained electrons, or you can have a positive ion where the atom has lost electrons, and it might have lost 1 or 2 or 3 or something else like that. Now there's probably, it's probably logical to say that there's going to be a limit as to how many electrons an atom is easily able to lose, at which point gaining some electrons would make more sense. And we're going to be running into that a little bit. And then this idea of a stable octet. Now again, I want to say that a stable octet is nothing magical. It's just a pattern that we've noticed where if an atom has 8 valence electrons, then it is fairly stable. It has a stable arrangement of electrons. And really what it comes down to is that probably the best idea, or the best way to think about a stable octet, is that it has the same electron arrangement as a noble gas. Noble gases are column 18. They do not react, and there are no known naturally occurring compounds of those noble gases. There are a few short-lived compounds that we've managed to produce. I will say we as if I had something to do with it. But the reality is chemists have been able to produce some compounds with noble gases, but none of them live very long and none of them are naturally occurring. So we want to work with the periodic table because that's going to be our main tool for almost everything that we do in chemistry. So we're going to start with sulfur. We did the Bohr diagram for sulfur a little while ago, so we're just going to jump into it, copy and paste, yeah. That's the Bohr diagram for sulfur. 6 valence electrons, 2 in the first, 8 in the second, 6 in the third. If my goal in a stable octet is to get 8 outer electrons, there's 2 options for doing that. One is I could add a couple of electrons, 2 specifically, or I could take away 6. Well, adding 2 is going to be simpler than taking away 6. So what's going to happen with those 6 valence electrons is we're going to add 2 more, at which point I will have 8 valence electrons. I will have that stable octet. So when I'm drawing the common ion, or the Bohr diagram of the common ion of sulfur, and you're going to see that phrase, common ion, and all that means is that what do I do to get a stable octet? What's the charge in that thing? And that's going to be the common way of doing it. I'm going to add 2 electrons. They're going to go in that outer orbit, in that outer energy level, so that all the electrons are paired up, and then I can easily see I've got 2, 4, 6, 8 outer electrons. They don't have to be a different color. Obviously I did that just so they stood out and you could see them more easily. But now I have stable octet. We're not going to worry about it today or right now, but it is important to understand that those electrons do have to come from somewhere. It's not going to be a thing that we have to worry about for this topic, but as we get talking about other things, as we get talking about how that electron, or how that atom gains 2 electrons and where those electrons come from, we do have to remember that all those electrons need to be accounted for. They do have to come from somewhere. If I go to calcium, now we haven't really been doing Bohr diagrams of elements number 19 and 20, potassium and calcium. I've been doing mostly the first 3 rows, but I thought, just so you have it, we should be doing 19 and 20, because every once in a while I do say up to 20. So here it is. If you were to look at the electron arrangement, there's 2 in the first, 8 in the second, 8 in the third, and then finally 2 in the 4th energy level. And yes, that runs into something that we said about Bohr theory a few videos ago, but we're going to bring it up now because it doesn't matter right now. So with 2 valence electrons, if I'm trying to get to 8, if 8 is my stable arrangement, 2 options, lose 2 or gain 6. So if I lose 2, seems a little bit easier. then I'll have 8 valence electrons, because I will lose not only those 2 electrons, I will lose that entire energy level. So when I'm asked to draw the common ion of calcium, I'm going to take away those 2 electrons to get to that stable octet. Take away the electrons, that energy level. It's never a thing anyway. It's not a physical structure, of course. It's just a energy level. That's now gone, or at least not visible. It's still possible. But now I've got a stable octet for calcium, 8 electrons in the outer arrangement, or in the outer orbit. Now, similar to sulfur, where the electrons had to come from somewhere, if calcium is going to lose electrons, they have to go somewhere. They can't just go off into the ether or disappear magically. They do have to go somewhere. Now, you might be wondering, is that all there is to it? And the short answer is, yeah, it is. That's really all there is to it. But there are a couple of qualifiers, if you will. And that is, not every atom has a common ion. We're going to deal with ones that do. But we saw before that the cases are a little bit more complicated. However, we know how to draw Bohr diagrams for the first 20 elements. Those have a common ion, so yeah, for our purposes, it really is that simple. But the other thing of it is that some atoms don't actually make ions all that regularly. I mean, we can force it on them, but they don't really have a common ion. And then, whoops, go back up. Some will do a stable octet in a different way. So they're not going to do it by losing or gaining electrons. Okay, well, if it's so limited, then why do we bother? Well, the fact is, it is. There are enough elements that have a common ion that it is worthwhile for us to know how it happens and what happens to it. It also gives us a good basis for some of the other things that we need to be doing. And then we have to worry about this, or I shouldn't say worry, have to deal with this notion that there is a pattern that stable octet helps us to understand. Not fully perhaps, but at least gives us something where we can predict, and that's important for us. And as I mentioned, there are elements that form their stable octet not by losing or gaining electrons, but by doing something else, which we'll talk about in a little bit. Okay, so if you don't have a Bohr diagram, can you predict the common ion? And the answer is yes, using the periodic table. Once we understand the patterns in the periodic table, then that's going to be the way we use it. However, our job right now was common ions, Bohr diagrams of those common ions, so that's what we're going to be doing. Okay. As I said before, I'm not a huge fan of Bohr diagrams, so we won't be drawing them a lot, but you do need to be able to draw a few of them. Okay, so here's what we talked about today. Those are the things that you will be asked to do, and then we'll talk to you another time.